The Antarctic Impulsive Transient Antenna, ANITA, has spotted two events which may be evidence of new physics. We nickname this type of event Alpha, November, India, Tango, Oscar, November, or ANITons for short. In this talk, we will investigate the possible origin of these events and the feasibility to search for ANITons using the second generation Extreme Universe Space Observatory on a superpressure balloon, the EUSO-SPB2 mission. This talk is based on work in progress in collaboration with Atri, John, Angela, Halsey, Ina, and Tony. ANITA is a balloon-borne instrument that detects polarized radio emission from the electromagnetic component of cosmic ray showers in the atmosphere, either reflected from the ice at the South Pole or arriving without reflection from events near the horizon. It also detects upward-going showers produced by tau leptons generated from the interactions of Earth-skimming neutrinos. ANITA has observed two anomalous events which qualitatively look like upward-going extensive air showers initiated by energetic particles, the average energy being roughly 500 PeV. These particles emerge from the ice along trajectories with large elevation angles, roughly 30 degrees above the horizon. While in principle this type of event has been anticipated as a result of astrophysical tau neutrinos converting to tau leptons during Earth passage, the origin of ANITA events remains intriguing because for the angles inferred from ANITA observations, the ice would be well screened from upgoing high-energy neutrinos by the underlying layers of the Earth, challenging explanation based on the standard model of particle physics. More concretely, for a neutrino of 500 PeV, the mean free path on rock is about 600 kilometers. This means that the course length these neutrinos should have traversed is equivalent to 10 to 12 standard model interaction lengths. Indeed, under conservative extrapolations of standard model physics, there is no particle that can propagate through the Earth with a probability larger than 10 to the minus 6 at these energies and exit angles. Although systematic effects of that analysis cannot yet be completely discarded as the possible origin of the ANITons, the door is open for speculation. Remarkably, beyond standard model explanations are already tightly constrained. For example, isotropic fluxes of astrophysical neutrinos, either active or sterile, or any other exotic particle that couples to the tau lepton through suppressed weak interaction cross-sections cannot be responsible for the ANITons. An interesting speculation is that the two ANITons could have similar energies because they result from the two-body decay of a quasi-stable heavy sterile neutrino, itself gravitationally trapped inside the Earth. The neutrino decays into a Higgs boson and a light tau neutrino, and the latter interacts in the Earth crust to produce a tau lepton that in turn, on decay, initiate an atmospheric upgoing shower. The fact that both events emerge at roughly the same angle from the Antarctic ice cap suggests an atypical dark matter density distribution inside the Earth. Another unsettled challenge facing this model concerns the trapping of a sufficient amount of sterile neutrinos inside the Earth to accommodate the ANITon event rate. However, an intriguing outcome of this idea is that it can be linked to the CPT symmetric universe. We know CPT is the one symmetry the universe must never violate, and therefore the matter-antimatter imbalance in the universe is a fundamental mystery. Right after the Big Bang, matter and antimatter should have been produced in exact same quantities, both should have been annihilated together, and their mass should have been converted into photons. Therefore, no matter and no antimatter should remain in the universe today, and we should not even exist. However, we know this is not the case. We are right here, made of matter, and the primeval antimatter has gone. The question is why? One possible solution is the CPT symmetric universe, first idealized by Sakharov in 1967 and more recently worked out by Boyle, Finn, and Turok. To restore the matter-antimatter asymmetry, Sakharov postulated that the universe was made not of a single entity, but a verse-antiverse pairs originating from the same Big Bang singularity and having two arrows of time in opposite direction from the instant t equals 0. The CP symmetry violation in our twin antiverse is opposite, in the sense that antimatter prevail over matter there. Now, what this has to do with ANITons? Okay, so let's assume that the matter fields are those of the standard model. Now, if neutrino get Majorana masses, then we have a quasi-stable dark matter candidate, the heavy right-handed neutrino. So, once we have this free quasi-stable massive fermion living on the background, we can calculate the dark matter yield, which is this dimensionless ratio. The ratio in the early universe of the number density of this dark matter particle, according to us at late times, over the entropy density of radiation. And this is given by some dimensionless number that depends on the effective number of degrees of freedom times the ratio of the mass of the dark matter particle divided by the Planck mass to the 3/2. Now we can ask ourselves, what would the mass of the dark matter particle has to be in order to give the right abundance today? And the answer is, it has to be 480 PeV. Therefore, modulo uncertainties in ANITA observation, this is twice the energy of the ANITons. Okay, so rather than to keep speculating and discussing model building, it seems more conservative at this point to depend on experiment, if possible, to resolve this issue. In 2022, the EUSO-SPB2 mission will monitor the night sky of the southern hemisphere to pioneer Earth orbiting observation of cosmic rays of very high to ultra-high energies, and to search for upward-going showers originated in tau neutrino interactions. A launch from NASA's Wanaka facility is motivated by the opportunity for a flight of up to 100 days. Wanaka lies under a stratospheric air circulation that forms each fall and spring. During the southern hemisphere fall, this wide river of high thin air circles the southern globe to the east at 50 to 150 kilometers per hour. A March-April launch window can insert the balloon into this circulation. The superpressure balloon is sealed. At float, it expands to a maximum constrained volume with a slight overpressure that remains positive at night to maintain the fixed volume. Hence, the balloons float at a nearly constant altitude. In the absence of technical issues, EUSO-SPB2 can remain aloft almost indefinitely. The payload, which is shown in this figure, is now in the design and fabrication stage. It features a pair of telescopes, one looking down on the atmosphere with an optical fluorescent detector from the near space altitude of 33 kilometers, and the other looking towards the limb of the Earth to observe Cherenkov signals. Both telescopes are based on Smith optical design of spherical mirrors with large field of view. For a down pointing, that is the nadir mode, the field of view open angle is roughly 12 degrees. The telescope has a larger field of view for limb observations. Observations can only be done on clear moonless nights. EUSO-SPB2 will fly in the southern hemisphere and thus it's subject to less light pollution. A thorough study suggests that a 50-day flight launched at Wanaka, which is at a latitude of 45 degrees south, during, of course, the March-April window, would see about 190 to 260 hours of dark time. And this depends on when the launch happens relative to the moon phase. For a 100-day flight, the fluctuation would smooth out a bit, and so about 500 hours would be a realistic number of dark hours, with no moon and between the end and start of astronomical twilight at 33 kilometers. We still have to correct for cloud coverage, and so the effective lifetime will be about 360 hours, and this will be for a total of a 100-day mission. For a nadir pointing instrument that has a constant field of view, the instantaneous observational area, and this is ignoring the Earth curvature, is a circle on the ground that has a radius equal to the altitude h times the tangent of half the field of view. The instantaneous observational area of the fluorescent telescope is then 32 kilometers squared. When this area is combined with the effective observation time, which is 360 hours, we obtain the total expected exposure, which is roughly 10 to the 4 kilometers square hour. And this is about a factor of 5 larger than the net exposure collected by ANITA-1 and ANITA-3 payloads. While the area is important, we have also need to consider differences in geometric factor, which bring in the differences in the acceptance solid angle of upward moving extensive air showers. Since ANITA is detecting ANITons near threshold, the acceptance is defined by their ratio of, by their radio Cherenkov angle, which is about 1 degree. To make a comparison, here are some simulations run by John that show how a 600 PeV ANITon signal will look like in EUSO-SPB2. For the optical Cherenkov signal, the mean angle is also about 1 degree, yielding a cold solid angle of 10 to the minus 3 steradians. So this would be the acceptance solid angle near threshold. However, for the brighter showers that we have here, the acceptance angle gets enhanced, as now we can measure the profile down into the tail of the Cherenkov profile, leading to a wider angular width for these extensive air showers. Halsey, John, and Tony derived a formula to estimate this enhancement. For EUSO-SPB2, this gives an effective Cherenkov angle of 4.5 degrees, which implies a geometric factor of about 20 with respect to ANITA. The photon spectrum has a peak at 340 nanometers and is almost independent of aerosol attenuation effects. So here is the take-home message. ANITons observed at the South Pole remain a mystery. EUSO-SPB2 will have an ANITon exposure above about 100 times ANITA. Since EUSO-SPB2 observation will be done over the ocean and using different detection techniques than those used by ANITA, detection of a single ANITon will discard the hypothesis that the anomalous ANITA events were driven by systematic effects. All in all, EUSO-SPB2 will provide a unique probe of physics beyond standard model.